So, factorials. So when you see this, and you're working with sequences and series, it doesn't mean 4. This is for factorial. Mathematically, it means, so here's what factorial means. It means you start with the number 4, and you're going to multiply down. Starting with 4, you're gonna multiply down by each successive counting number, decreasing by 1 until you get to 1. So this very simple definition is crucial that you have this, because when we start getting n's involved, you have to make this transfer when n's are involved. You start with that number, and you continually multiply by 1 less, then 1 less, then 1 less, until you reach 1. So 4 factorial is 4 times 3 times 2 times 1, and that's 24. Okay, by definition, we won't get into why this is true, but 0 factorial is not 0, it's actually 1. We don't, that's a can of worms. We don't, just take it for what it's worth, and we'll move on. Okay, so find 6 factorial by hand, okay, by hand. What is 6? Write it out, what it means first. Write out what 6 factorial means, and then determine what it's equal to. So you should have written out 6 times 5 times 4 times 3 times 2 times 1 equals 720. So notice, what's the relationship between 6 factorial and 4 factorial?
6 factorial equals 6 times 9 times 4 factorial.
Do you see that? Yeah. Do you see that 4 factorial is a factor of 6 factorial? So if you took 6 times 5 times 4 factorial, you'd have 6 factorial. Do you see that? It's in there, right? Every factorial of a value less than the one you have is a factor of the one that you have. So 3 factorial is a factor of 6 factorial. There it is right there. 5 factorial is a factor of 6 factorial. There it is right there. So use that, what we just talked about, to figure out what this is. What is 28 factorial divided by 25 factorial? Can you figure out what that is without doing a whole lot of writing? Right? Can you figure that out, what that is, without writing 53 values down, right? Use the fact that we just talked about. You could write a little bit to help you. Just don't write out 53 numbers. Don't write out 28 factorial explicitly. Don't write out 25 factorial explicitly, but how can we, through an understanding of factorials, get what this would be pretty quickly? Hunter's got it. Anyone else got it? Will, tell me.
I think it's just 28 times 27 times 26.
Okay, because 28 factorial is the same as 28 times 27 times 26 times what? 25 factorial. And if we divide by 25 factorial, what happens? Gone, right? That's 1. And you're left with 28 times 27 times 26. Do you see it? Does it make sense? That should be, this is what comes up in factorials all the time, and you have to have this correct mental image of what's happening. (25 factorial is part of both of those. Okay, so then figure out what this is. Here's a sequence. So now I got a sequence, right? Here's a sequence. 2n minus 1 factorial over 2n plus 1 factorial. So you have to be really solid on 1 factorial means to make sense of this. So could we make a representation of that numerator? Could we write out explicitly what that numerator is saying? Who thinks they could do that? I know Hunter can. Can you do it, Ariane?
I just wrote out 2n minus 1
Okay.
times 2n minus 2 times 2n minus 3.
Okay.
And then I went to the denominator.
So where would I stop? Where does it stop? Just the numerator. Where do they all stop? Where do you stop multiplying? Right, so it's going to keep going until you get to, you're going to eventually get to 3, and then to 2, and then to 1, and you're going to stop. Does everyone see how that's explicitly what the numerator is? That's factorial. Do you see that? You take the number, and then you multiply by 1 less than the number. What's 1 less than 2n minus 1? 2n minus 1 minus 1, or 2n minus 2. We're doing the same thing we did up there. It's just the nth term of the sequence, right? So now if you didn't get that before I wrote it down, now do the denominator. Everyone do the denominator. What will that be? Write out several terms. Or factors, I should say. Write out what it means. Guadalupe, did you get it?
Bottom, which would be 2n plus 1 and 2n. The next one.
Okay.
2n minus 1.
Okay.
It's the same thing as the first term from the top.
Right. All the way to? Until when?
One less.
It's factorial. When do you stop multiplying in a factorial? When is that? The last, you always multiply down until you reach 1, and then you stop. So now what happens here? So what do you notice about the denominator compared to the numerator? Ruth?
It's pretty much the same, so it's going to cancel out the whole numerator with some part
What is that right there?
the same as
That's 2n minus 1 factorial. So 2n minus 1 factorial is a factor of 2n plus 1 factorial. Eventually you get to 2n minus 1 2n minus 1, and then the rest is the same, 2n minus 1 factorial. So what does this equal?
1 over 2y plus 1.
And now you guys have some expertise at sequences. So these are equivalent, right? So this factorial expression is equivalent to this expression. Tell me about the sequence. Joseph, can you tell me about that sequence?
No.
Uh-oh.
The limit.
These guys are saying it converges to 0 as the limit as n goes to infinity, right? Because that's essentially 4n squared plus 2n has plenty of muscle power to get to 0, right? As n gets big, right?
I do see it. I was just on the spot.
No problem. I left it open. I left it kind of the question open-ended, right? But the main question we have when we come to a sequence is, what's the limit as n approaches infinity? That's really what we want to know. Does it have a limit? And so this one, particular one has a limit, 0. Questions on factorials? Yeah, please. What? That's just another way to write limit. So this is another way to write a limit. So this thing will approach 0 as n goes to infinity, which is exactly the same as writing this. It's just another way to write it, that expression will approach 0 as n approaches infinity. Other questions? Okay, so what do we say? A sequence is what, and a series is what? This is key.
Sequence is a list of terms, and a series is a sum of those
Right,
terms.
so talking about this stuff is totally irrelevant if we don't have this simple fact first. A sequence is an ordered list. A series is the sum of the numbers in the sequence. So given a sequence AN, the associated series is this: A1 plus A2 plus A3 plus A4, on and on and on. So especially, so we're going to be talking about infinite sequences, an infinite series. So that's why it's dot, dot, dot. You keep adding terms forever. But we know, what do we have when all the terms kind of look alike? We have our notation, right, for that. And that's summation notation. That allows us to really just write an example of what the terms look like just once. And then we know that it means we're writing out a bunch of those. Okay, so this is what it is. And it's going to start at 1 and keep progressing up to infinity. And when you write this, this notation here, so when you see this, you need to think this. Because that's what it means. That's what that notation means. It means let n equals 1. You get the first term of this sequence. Then let n equal 2. You get the second term of the sequence. We're going to add it on to the first term. And then n equals 3. That gives us the third term of the sequence. We're going to add that one. And then n equals 4. Etc. Crucial, right? This is so the next 3 days of your life are going to be immersed in these things right here. So every time you see one, you have to think of it's the sum of many terms described by that sequence, that whatever a sub n is. Okay, so here's a sequence, 2n minus 1. So the corresponding series would be this. I want you to write out what it means. Explicitly write out what. When you see this, what do you think? You see this, you think what? Write it out. Allison, did you get it?
2 times 1 minus 1.
Yeah.
Number.
Yeah, uh-huh.
So 2 plus 3.
Try again.
Oh, 1.
Okay, all right.
1 plus 3 plus 5 plus 7.
Right. So how many had that before I put it up there? Not enough. Okay, so this is what this means, right? This is a sequence. The first term of the sequence is when n equals 1. The second term of the sequence is when n equals 2. The third term of the sequence is when n equals 3. And the series means you're going to add all those terms of the sequence up. So tell me what will happen when we add up all these. We're going to keep going. This is an infinite sequence, and we're going to add up all the terms. What's going to happen? Alvaro? Yeah, right. Badly, right? Because each number that we add keeps getting, the numbers that we're adding are going toward infinity, and then we're adding them together. Okay, so this is what we call a divergent series. Why? Because this thing is going to get really, really big. As big as you want and bigger than that. Okay, how about this? So practice. What would this be? Write out what the meaning of this is. If the sequence is 1 over 2 to the n, and you see this right here, the sum is n equals 1 of bn, what does that mean? Write it out explicitly. If you see this, you think what? Write it out. Okay, Adrian, you're up. Yeah, so 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32, etc. Okay, what about this? So we can think about this. This is kind of like the turtle that's walking across your backyard. You guys all have a turtle walking across your backyard, right? You all have a backyard, right? Okay, so here's the turtle. Some people don't have a backyard, and that's okay. That's okay. All right. Here's the turtle. And what does he do first? His first step in his journey is what? Halfway across your backyard. Boom. But now he's getting a little tired. What's his next step? He goes another quarter across your backyard. So where is he now? He's at 3/4 of the way across. So that's what's called a partial sum. This is the second partial sum. He's 3/4 of the way. And then but now he's getting really tired. What's the next step? He goes an eighth, and that puts him where? 7/8 of his way across your yard. So that third partial sum is 7/8. And he keeps doing this. So every time he takes a step, or makes his next part of the journey, where is he relative to where he was before? He's always half the distance to the other end, right? He always is walking half the distance to the other end of the backyard, right? And then he's going to do that forever. So if he does that forever, what will his result be? She said 1. He makes it 1 distance across the backyard. If he does it forever. If he keeps going half the distance that he was before and never ends, then he will reach the other end. But that's only if he goes forever. If he keeps taking that 1/2 step and never stops. The limit of that, or that sum, is 1. But he has to take an infinite number of steps.
So it's still considered a convergent series. It's just convergent to 1.
Yes. So now this is what we call a convergent series. This is a convergent series because the sum of all the terms equals 1. The sum of all infinitely many terms is 1. But if you're to cut it short anywhere, it won't be equal to 1. If you cut it short at 999 trillion terms, it will be very close to 1, but it won't quite be 1, right? So you need more terms, right? So if you can add infinitely many of those terms together, you would get 1. So that's why it's a limit. It's like the feeling of a limit, right? So you can add an infinite number of things together and get a finite value. We've seen it before. When did we see this before? This idea. What did we do where we saw that? What's that? It wasn't areas.
It's just integrals.
Which kind of integrals? Remember? What's that? Remember the improper integrals, where when we go from, say from 1 to infinity. This is the same idea, right? So this is like those improper integrals where we went from 1 to infinity. And sometimes we got these to be finite values, right? It's a very similar idea. So rather than looking at this function, the integral of a function, it's now we're adding discrete terms. But if this, and we'll get to this in a second, so let's just keep going. But so this is very similar to improper integrals, which we saw some were divergent, some were convergent. Okay, another one. Go. You see that? You think what? No, this is not equal to 5. You see, when you see this, it's equal to what? Okay, careful. We're talking about a series now. You have to, in your mind, you have to distinguish between series and sequences. Series is built from a sequence. Here's the sequence. Tell me what the series is. Write it out explicitly. Okay, Kaylee, you're up. Can you tell me? What does that equal? 5 sevenths times 1.
5/8.
5/8. Is there more to it? So tell me. N is 2, right? What is, if n is 2, what do we get? 20. 20 elevenths. Let's just do one more. Anyone got the third? Right. And how many of these are we adding up? A lot more, right? A lot more. Okay? And so now we can think about our skill set at what? Thinking about what does Cn, is that convergent or a divergent sequence? She says divergent. Divergent sequence?
Yeah.
Everyone's nodding? It's a divergent sequence, Cn. Everyone, yeah? Sequence, divergent sequence. I thought we were supposed to be expert at sequences by now. It's not a divergent sequence, you guys. Talking about the sequence, Cn. You have, see, a sequence is a list. A series is the sum. I'm talking about the sequence, like your homework this weekend. Is that divergent or convergent?
It's convergent.
That's convergent to what? To 5. Right? Those terms get closer and closer to 5. So either you think of this as a rational function with the degrees being the same, and you take the ratio of the leading coefficients, or you can do that, divide by everything by n squared, remember that? Divide everything by the highest power of n. And then you get 5 over 1 plus 7 over n squared, which gets very small as n gets big, so it goes to 5. So let's think about the series then. So then the series, 5/8 plus 20/11 plus 45 over 16 plus, when the n gets large enough, what is this sequence, the series, like then? So if n gets really, really big, we go down the road, say a trillion or a quadrillion or a quintillion terms. Now what are those terms like?
It's gonna get really close to 5.
Those terms are going to be really close to 5, getting closer and closer and closer to 5. And when we get to a quintillion, which isn't even close to infinity, it's going to be so close to 5. These are going to be essentially, I'll put them in parentheses, meaning essentially 5. And how many of those will we have? So now let's talk about the series. What will the series be like? That'll be infinity. Why? Because you're going to add an infinite number of essentially 5s together. You're going to get out to a number that n where it's essentially 5, and then you're just going to keep adding numbers that get closer and closer and closer to 5, which is essentially just like adding 5 over and over and over again. Divergent, because you're just going to, in essence, you're just going to be adding an infinite number of 5s together. But the sequence is fine. The sequence converges to 5, right? Those terms are getting closer and closer to 5. Okay, so this brings up the first kind of incredibly important principle about series. When do series converge? When does a series converge? Based on its sequence.
When
the sequence goes towards 0.
Okay?
I was just gonna say when the denominator is larger than the
So denominator is larger than the numerator. Well,
I'll just say what he said when it goes to 0.
when the sequence goes to 0. When the sequence goes to 0. Yeah? Okay, so this is called, so let's say this. Instead of when does a series converge, let's talk about when does a series diverge. When does a series diverge? What's that? When the sequence is convergent, the series diverges?
When the sequence is either divergent.
Was that?
When the sequence is anything greater than 0.
Yeah. So right, if the sequence does not, if the limit of the sequence does not equal 0, then what's going to happen? You're eventually just going to add the same number, non-zero number, over and over and over again when n gets really, really big, just like that last example that we saw. But also, if the limit doesn't exist at all, like you saw the ones that alternated in your homework, we talked about those, like 1, 0, 1, 0, 1, 0, those sequences. Also, those series do not converge. So this is the divergence theorem. If you have a limit of a sequence that doesn't go to 0 or a limit that doesn't exist, that corresponding series is divergent. So it's like we just knocked out most series in the world. Now we understand most series in the world. If you have if your sequence doesn't go to 0, that series is divergent. You don't have to talk anything more about it. Or if the sequence doesn't have a limit, then the series is divergent. So what's the more interesting case? So now, that's technically the divergence theorem, but what's interesting? What are we going to spend most of our time talking about? If what? If the limit does equal 0, then what? Then the series converges. Is that right? Is that right? Adrian? Sometimes. Okay, so one thing we know for sure, that's necessary. That's got to be true. If this is not true, if this goes to some other number other than 0, or the sequence diverges, then we know that the series, we just said, the divergence theory says. So we know for sure this is necessary. Is it enough? Is it sufficient? Is this enough to say that, so this is conjecture. So we had an example of a sequence going to 0 and the series converged to 1. Does that mean that anytime the sequence converges to 0, the series is going to converge to a finite number? Jury's out, right? Jury's out. All right, let's look at another example. So let's look at something called the Harmonic Series. See this? Think what? Go, write it out, practice. You see this? This is called the Harmonic Series, 1 over n. You see this? You think what? Who's up? Jacob, tell me.
When I see that, of course, you get the 1 over 1 plus 1 over 2 plus 1 over 3, and so on.
Right, good. This is what you should think when you see that. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. How about the sequence? Tell me about the sequence AN. Yeah?
The sequence is less than 0.
The sequence is less than 0.
Because like as you keep going on to infinity, like you just keep decreasing.
Okay? So when we talk about a sequence, we talk about the limit of that sequence as n approaches infinity. So what is the limit of the sequence?
0.
Limit is 0, right? Certainly n just gets, like you're saying, n gets larger and larger. And so the limit of the sequence is 0. So what about the series? You think it adds up to 2? They're guessing that adds up to 2. Okay, let me show you something. So here, This is a different sequence, and it's going to help us to analyze this first one. There's a different series. It's going to help us to analyze the first one. Okay, so would you agree that these are the same, right? So this is equal to 1, right? Do you see that? 1/2 plus 1/4 plus 1/4 is equal to 1. No, let me do this different. Half. This is equal. This will be easier. This is equal to 1/2, right? And do you see? So how do those two terms? How does 1/2 compare to these two terms? 1/3 plus 1/4. How does that compare to 1/4 plus 1/4? Greater than or less than 1/2? That's greater than 1/2, right? And what about 4 1/8? What is that equal to? 1/2. How about 1/5 plus 1/6 plus 1/7 plus 1/8? How does that compare to 1/2? Greater or less than 1/2? Greater, right? 1/5 plus a 6 plus a 7 plus a 8 is greater than 1/2. Why? Because it's greater than 1/8 plus 1/8 plus 1/8 plus 1/8, which is 1/2. How about 8 1/16? How much is that equal to? 1/2. And then what about 1/9 up to 1/60? If I did 1/9 plus 1/10 plus 1/11, excuse me, or etc. Greater than 1/2. Okay, so what am I going to do? I'm going to take the next 16 terms, which are 30 seconds, and that's going to equal 1/2. I'll take the next 16 of these, and that'll be greater than 1/2. You see what's happening? I can always get another set of values that are greater than 1/2. I just need to take twice as many as I took before, but I'll never run out because it's an infinite series. So all I have to do now is take the next, here, these are 8 terms. If I take the next 16 terms, the sum of those will be greater than 1/2. And then if I take the next 32 terms, the sum of those will be greater than 1/2. And then if I take the next 64 terms, the sum of those will be greater than 1/2. Convergent or divergent? You can always find enough terms to get a chunk that's more than 1/2. So you keep adding values that are more than 1/2 every time. So the series goes to 0, but the sequence diverges. Since this right here is greater than this diverges. Or goes to. That's an arrow, true an arrow. So the harmonic series is a divergent series such that the sequence has a limit of 0. So this answers our question. If an goes to 0 as n goes to infinity, then tell me about the corresponding series. It may or may not converge. Necessary, but not sufficient. Necessary, but not sufficient. It's got to be true for the series to have any kind of fighting chance. If the sequence does not go to 0, game's over. If the sequence does not go to 0, it's a divergent series. Game's over. Now, if the sequence does go to 0, then maybe it will converge, maybe it won't. Here's an example of one that doesn't converge. So this is the first kind of major principle about series that you have. It doesn't matter to talk about anything else unless this this makes sense. When you see a series and you're asked, does it converge or not, the first thing you need to know is, does that sequence go to 0 or not? If it doesn't go to 0, you don't do any more work. It's divergent. Make sense? So you got to have a convergent sequence, convergent to 0, and then the series is worth talking about, whether it converges or not. Okay, so let's go back and talk about first type of series is geometric series. Back here somewhere. So geometric series is a series of this form, a times r to the n minus 1. Okay, see this? Think what? Write it out. What is this series? What does that notation mean? That notation means what? A and r are some constants. A and r are some constants. Andre, you're up. A and r are constants. So what does this equal?
1, but yeah, it equals 1 plus AR plus AR squared plus AR to the third power.
Almost, what's the first term again?
A.
Yeah, so we got it. A plus AR squared plus AR cubed.
Oh, so it's not AR quantity. So it's
No,
not
if it were, there'd be parentheses, right? So exponential power comes first, then multiplication. Yeah. Okay, so this is the form. This is a geometric series. A plus AR squared, AR cubed, etc. Okay, so you remember, so we're talking about the sequence needs to go to 0 for the series to have a fighting chance, right? The sequence has to go to 0 for the series to have any chance of converging. So what does this kind of remind you of in terms of sequences? Remember what kind of sequence this is like? What's that? Yeah, p to the n. Now instead of calling it p, we're calling it r, right? So now r is taking the role of p. When did those, so we need the sequence to converge to 0. When did the p sequence converge to 0? When?
between -1 and 1.
Right. When that p value, which is now an r value, was between -1 and 1, that sequence will go to 0, and then that series will have some kind of fighting chance of converging. So we want to know. So we know that when r is between -1 and 1, the sequence will go to 0, but what we really want to know is for what values of r does the series converge? So our candidates for r are going to be between -1 and 1. So is it going to be for all of those or just some of those that the series converges? Does the problem make sense? Does the situation make sense? So let's find out. So this is what we're gonna do. So we're gonna take the series. And we're gonna look at so this is the original sequence, a r to the n minus 1 for the series. And we're going to look at another series, which is r times that. So what will be the first term of that series? AR. So I'm gonna line it up with the one on this one. So I'm gonna start my first one here, right? And then what will the next term of that one be? Okay, so look what happens. So if we multiply by r, then we get what? We get all the terms after the a term. So what I'm going to do now is I'm going to subtract. I'm going to subtract the bottom one from the top one. And on the top, I'm going to get what? Oh, I hope I'm doing this right. I might have to check my notes. But so what I'm going to do, when I take that top one minus this one, I'm going to get a. And then here I'm going to get, yeah, I got it. Okay, so that's right. So it's going to be this minus this. So it's going to be, I'm bringing this subtraction here over this side here. It's going to be a r to the n minus 1 minus, sorry, the sum, minus the sum of r times a So I'm going to bring this r out. I'm going to factor out the sum. And this is going to be a equals the sum of a r to the n minus 1 times 1 minus r. So this tells us what that sum is. What is it equal to? So that's our original sum that we were talking about, right? The sum of a r to the n minus 1. What is it equal to? Just kind of think of that as a number and solve for it. A over 1 minus r. Okay? And it does in fact converge as long as the sequence goes to 0. And that was, we knew that was from -1 to 1. But this little trick here, what we did, showed us exactly what number it will converge to. A over 1 minus r. So now I'm talking about the series, right? The series. It converges to this number when r is between -1 and 1. So a geometric series converges whenever the sequence goes to 0, because by our p sequence, right, we know that the sequence goes to 0 between -1 and 1. So as long as it's a geometric series that has a convergent sequence, that series will converge to a over 1 minus r. Now, you have to have it, you've got to get the form looking just like this for it to work, okay? It's got to be starting at n equals 1 to infinity, a r to the n minus 1. So let's do an example. Let's do the turtle example. The turtle example was in fact a geometric series. What was the turtle example?
1/2.
It was n equals 1 to infinity, 1 over 2 to the n. Now, we need to make that look just like this. A times r to the n minus 1. So we got to do some work on this to get it to look like a times r to the n minus 1. So the first thing we can do is say, what do we want to do, Ruth?
It would be 1/2 times 1 over.
No, but we got to get it to look like a r to the n minus 1 before we can. Are you trying to use this? We can't use this yet because we got to make it look like this. A r to the n minus 1. All we have is something to the n. That doesn't quite look like this yet. Once it looks like this, then we can plug and chug into the a over 1 minus r. So what do we have? We have 1/2 to the n. We need something times something to the n minus 1. So we need something times something to the n minus 1.
1 over 2 times 1 over 2 to the n minus 1.
So this, yeah, good. So this goes back to what does 1/2 to the n mean, and what does 1/2 to the n minus 1 mean? Well, how do you distinguish between 1/2 to the n and 1/2 to the n minus 1? How can you think about that? So who can explain what 1/2 to the n is? See 1/2 to the n? You think what? You see 1/2 to the n? What do you think?
1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2.
How many 1/2s?
N times.
N of them. So what's n minus 1?
1 less half.
1 less half. But we need n of them, right? So I can do 1/2 to the n minus 1, but then it'll be 1/2. I'll be 1/1/2 short. So then what's a? 1. That's the last one. You see? So now in both cases I still have n 1/2s multiplied together. But now it looks exactly like what we want it to look like. A r to the n minus 1. See what happened? So I just changed the form of it so that it looks like a r to the n minus 1. But what I really have in either case is n number of 1/2s multiplied together. I just pulled one out. I just pulled one out and made it separate, and then there's n minus 1 left. So therefore, this is it's a geometric. The turtle problem was a geometric series. Value of a was 1/2. Value of r was also 1/2. Does the sequence converge? Yeah, because r is between -1 and 1. The sequence converges. What about the series? Likewise converges to what? So now we can use this. A over 1 minus r equals 1/2 over. And what do we say about the turtle? If he takes an infinite number of those steps halfway to the other wall, he will get there. We got 1, right? So looking at the turtle problem in 2 different ways. Looking at it conceptually as always walking 1/2 the distance to the wall. He'll eventually get there if he keeps walking for an infinite number of steps. Here now this is applying geometric series, and we see we get the same result. The geometric series 1/2 to the n equals 1. Question on geometric series. Oh, all right, I had it all. Okay, so another example. This. I don't know my slides well enough. So let's work on this other example. So what's the goal here? The goal is to manipulate this thing, finesse it, to get it to look like something times something to the n minus 1. So we need algebra. We need good algebra knowledge of exponents to get this to look like something times something to the n minus 1. Can you do it? If you can do that, then we can analyze it as a geometric series. So let's just ideas. Anyone think they made progress? Ruth.
3/5. It's gonna be equal to
So what do you do? Tell me, explain everything you're doing there.
I just took 1 negative 3 out, so now the exponent is gonna change to from n to n minus 1.
Okay, so it's our first step is she wants to pull out 1 negative 3 in the numerator. So negative 3 times negative 3 to the,
N minus 1. And then,
see if you can go from there.
and then you just separate the multiplication, and it's gonna be negative 3/5 times negative 3/4, all that to n minus 1.
Does it work? Did she do all the math? Did she follow the rules? Is it a convergent sequence? What number are you looking at to see if it's a convergent sequence? Jacob, what are you looking at?
It's going to be greater than, it needs to be between -1 and 1.
What's it?
The, yeah.
Which one is that?
Yeah, -3/4.
Okay, so you're looking at the negative 3/4, so it's between -1 and 1. The sequence converges. What about the series? Yeah, so for these geometric series, anytime if it's geometric and the sequence converges to 0, your p-value or your r-value between -1 and 1, automatically the geometric series will also converge. To what? To what? Joseph, you don't have to do all the math in your head, but how would we get it?
Well, we would set it up with A on the top, so A would be -3/5
Beautiful, okay.
over 1 minus A minus 3/4.
Anyone have that? Is that 7/4? 21 120ths? Negative? Did I do the math right? Oh, but it would be 4/7. So it would be 12/35. I think it's negative because the denominator is positive. The numerator is negative. Yeah?
Is this an example of a series that converges but of a sequence that diverges?
You tell me. So you're asking if the sequence converges but the series diverges? So you want you think
as n
this?
goes to infinity because the denominator the numerator has a higher
So
higher exponent.
you're proposing that the sequence diverges but the series converges. Then you missed it. You missed it big time. The only way a series has any fighting chance to converge is what? You're probably not the only one, so it's good that we're going over it. The only way a series could possibly converge is if what has to be true?
The sequence converges as well.
No.
It's a chance to converge.
He said if the sequence converges as well. Is that true? The sequence has to go to 0. The sequence must go to 0. If a sequence doesn't go to 0, then what happens? In the end, you end up adding a non-zero number together over and over and over again. Is that going to converge? Remember our 5? Okay, don't forget this. Say a sub n goes to negative 1.5. Does the series converge? What's going to happen when n gets really, really big? We essentially are going to be, what's that series going to be like when n gets really, really big? Adding negative 1.5 over and over and over again. Will that series converge? No. It'll just go to negative infinity because you keep adding negative 1.5 over and over and over again. So, when can a series possibly converge?
When the sequence goes to 0.
When the sequence goes to 0. That's the only ones we want. Those are the only ones that are interesting, right? If the sequence goes to something other than 0, then you got to think of this. You're going to keep adding these terms that are getting closer and closer to a non-zero number. So if they're getting closer and closer to the same number, like 3 plus 3 plus 3 plus 3. Or this example, negative 1.5 plus negative 1.5 plus negative, on and on and on, right? Can't converge. That sum can't converge. The only possible way a sum can converge is if the terms of your sequence are getting closer and closer to 0. And then does it converge? Maybe. It has a chance. You're telling me there's a chance. Right? Okay, so this one. So when we're talking about geometric series, what about the sequence? This particular sequence. What does it do? Daphne, what does that sequence do? Negative 3/5, just the sequence. What's that? And how do you know that? Because why? Why does that sequence go to 0? Because r is between negative 1 and 1.
So if it's in that form, that's all we have to look for is that R.
Right. Because this is essentially a p sequence. It's just now we're calling it r instead. If that is between negative 1 and 1, then you essentially have that same p sequence that we talked about, that you worked on in your homework and we talked about Thursday.
If we manage a way of putting it in the same terms, like a times r to the n minus 1, but r is not between negative 1 and 1.
And what about the sequence and what about the series? What about this?
Don't know.
But what about the sequence? If it's not between negative 1 and 1, then what can you say about the sequence? Diverges. So what about the series? Has to diverge. The only way a series can converge is if the sequence goes to 0. It's the big point of the day. This is the one takeaway of the day. The only way a series could possibly converge is if the sequence goes to 0. But that's still not enough. It may or may not. Anything else that happens to that sequence, if it goes to a non-zero number or it diverges, then the series diverges. Will, did you have a question?
So, I kind of lost the importance along the way of a over 1 minus r. Is that, so are we saying this sequence we have here, when it goes to infinity, its overall value is negative 12 over 35?
You said sequence. What does the sequence go to as n goes to infinity?
That one goes to 0.
That goes to 0. So did you mean to say series?
Yeah.
Yeah, so the series. So now we have those terms that go to 0. Now we're going to add them all up.
Right.
When we add them all up, we get that number. So if you can add all infinitely many number of that p sequence, you're going to get negative 12/35. If you add a gazillion of them, you'll be essentially at negative 12/35. You'll be very, very, as close as you want. You just as you keep adding more and more terms, you keep getting closer and closer to the negative 12/35. Right.
Just to kind of
Yeah, please.
hammer it home, we're going to get a sequence like this here. We're going to put it into the geometric, series. We're going to put it into the geometric form.
If it is a geometric
If
series,
it's a geometric
we're going to look at lots more kinds of series.
Okay.
But this particular example and the turtle one, these are both examples of geometric series.
And then we're going to look at the R and see if it goes to 0.
Right?
If it does go to 0, then we're going to use the form A over 1 minus R to see if it converges to some number.
No, it does. If in a geometric series, if that's ever between -1 and 1, it's a convergent series. The series converges. The sequence converges to 0, and the series converges to the value A over 1 minus R. It sums up to that amount. Good discussion. Feel like we're really getting it. Good. Okay. Talked about the harmonic series. What's next? Okay. So the geometric series is based on the P sequence. Okay? But then there's something called a P series, which is different. So this is would not be my choice of notation, but this is how textbooks do it. The P series is of this form. So they switch it. They switch it. So when the type of series that corresponds to a P sequence is the geometric series, where they use R, and then they call a P series and they make the P the exponent. So not well thought out, but we can learn it. We just have to be aware of that.
P sequence, and then I'll just say the P series.
The P sequence we talked about was P to the N.
Who came up with those names?
And so we know that goes to 0 when P is between -1 and 1, and this is the basis for our geometric series, which is A R to the N minus 1. So here, P is like R. Okay, the P series is like the sequence, what we talked about, 1 over, see, I flip them. So when did 1 over N to the R go? Sorry. If what? It was greater than 0. Remember this? And so now this type of sequence corresponds to what textbooks call the P series. When does that converge? When P is greater than 0? What do you get if P equals 1? Harmonic. So the harmonic series is a particular example of the P series. It's the P series when P equals 1. Divergent or convergent? We show this one diverges, right? You just keep taking double the number of terms as before, and you can keep adding like numbers greater than 1/2.
So it's exactly just like the rule that we have.
Yes, that's right. So when does a P series converge? We want this to get to 0 faster than that. We want the denominator to be bigger. So, yeah. If P is greater than 1, then the P series converges. It's just like what what Ruth said. This is the same situation as our improper integrals now. Remember we talked about the improper integrals. When that exponent is greater than 1, that rate function gets down to 0 fast enough for the sum to converge. But if the rate function is 1 over n to the 1 or something less than 1, then yes, the rate function gets to 0. Yes, the sequence gets to 0, but not fast enough for the sum to converge. Same principle, exactly the same principle. Okay, questions on that? So example. Is it a p-series or geometric series? Is it a p-series or a geometric series? P-series. So the reason you know is n is in the base. If n is the exponent, then that might be a geometric series, right? Because we need something to the n minus 1. Something to the n, which we can manipulate to get n minus 1. So it's when your exponent's in the power that you have a geometric series. See, it's right there. When your n is the base, that's a p-series. So this is 500 over n cubed. Is that, so you see that, you think what? Let's practice again. Write out what it means. Write out what it means, 500 over n cubed. Hey man, can you tell me? What does this equal?
500 over 500 plus 500 over 8 plus 500 over 16. No. 27.
Good, etc. And then, conclusion, convergent or divergent?
Eventually convergent.
It's not eventually. We're saying when you add all the terms together, is it going to converge or diverge? Like, yeah, so when you add all the terms together, you get a finite value because it's a p-series with n greater than 1.
Is there like a formula that we use, you know how we used one for the geometric series?
Right.
Actually found.
Okay, so when it comes to actually finding what the sum is, the only time that we do that exactly is with the geometric series. We have that formula. With any other one, it's really about getting close enough. So how would we get a good estimate for what this is? What would we do? But then what would we do? Like if you're on you absolutely needed to figure out what this, we know this sum converges to some number, and you were desperate and you needed to know what it was, how would you find out? No? How? What are you going to do? Plug in 1,000 into this? Will that be an estimate for the sum? What will it be? So yeah, if you plug in a really big number for n, you expect to get some, what do you expect to get?
Goes to 0.
Right, we know this sequence goes to 0. So for a big value of n, you're going to just get a value very, very close to 0. And now we're talking about summing up all the terms. And you desperately need to know what all the terms summed up would be. What do you do? Jacob?
I was guessing something with factorial,
No. What are happening to these terms as we keep adding? They're getting closer and closer and closer to 0. How can we get an estimate for the sum? What's that? What do you mean by that? We know the limit of the sequence is 0. So when you say that find the limit, what do you mean? How do you do that?
You go to the point where you start getting fractions that are close enough to 0 when you're adding them, so then you can kind of look at all that's happened before, sum
Okay.
that up, and that'll give you pretty
Yeah.
close.
Just start adding. Just start adding. And what's going to happen to the terms? They're going to get so close to 0 that eventually they're just going to add on such a small amount that you don't care anymore. So you just start adding the terms together. And then whenever you're satisfied, right? So as those terms get closer and closer to 0, at some point you're satisfied that you have a number that's close enough to your sum. Does that make sense? Because those terms that you're adding are just going to become smaller and smaller and smaller fractions, closer and closer to 0. So maybe you want it correct to 10 decimal places. Well, eventually you're going to add enough terms that the terms after that will change the value past the 10th decimal place only. You see? Because they're so close to 0. Yeah. So you just start adding. You just start adding. Now this isn't a good example because of the 500 in there. Because this is going to take us a long time because these are going to be huge numbers at first. So maybe a better example of this, maybe just like 1 over n to the 4th. So what is it? It's 1 over 1 plus 1 over 2 to the 4th plus 1 over 3 to the 4th. Right? So how can we get an estimate for what that is? One plus 1 over 16. So notice we're at 1.0625. Now 1 over 81, 1.07 plus 1 over 256, 1.07875. So see even after 4 or so terms, 1 over 5 to the 4th, 1.08. 1 over 6 to the 4th, 1.08112. You see what's happening? The individual terms are getting really close to 0 because they're getting big fast. And so eventually these decimal places are going to get locked in. It looks like an 8 is a lock right now, right? So we know it's 1.08 something. Eventually that place is going to get locked. And it won't be influenced anymore by the terms that we keep adding. So it's how many decimal places do you want? One more. 10 to the 4th. So it looks like it's 1.082 something. So if you're satisfied with 3 decimal places for this sum, it's 1.082. Because these terms are getting small quick, right? And so we're going to just keep adding smaller and smaller values. For sure, we got 1.08 and probably 1.082. But for our purposes, we don't have, for the P series, we don't have a nice tidy formula that gives it exactly the way the geometric series does. Geometric series is kind of like the only one where we get this formula where we know what the sum of all infinitely many is very quickly like that. Okay? Yeah, please.
What if P less than 1?
What if P is less than 1? Well, how would that compare to the harmonic series? So if it was 1 over n to say the 1/2, then how would those terms compare to 1 over n?
You mean, oh, it's, and like into the 1/2.
So each one of those, 1 over n to the 1/2, how would those compare to all the 1 over n's? Greater or less?
Less.
1 over n to the 1/2?
Oh, greater.
Greater. So you have a harmonic series, and now you have one where every one of those terms is greater than the terms of the harmonic series. So what would happen?
Divergence.
Yeah, and this is an important concept. This is called the comparison test. So I think that's next. This is exactly what he's asking. What about 1 over n, say, to the 1/2? So look at 1 over n is 1 plus 1/2 plus 1/3 plus 1/4, okay? And 1 over square root of n would be 1 plus 1 over square root of 2. How do each of these numbers compare? Which one is bigger? The one on top or the one below? What's bigger, the one up top or the one in the below? One below. And what happens to the harmonic series? Diverges. Now you have a series such that every term is greater than or equal to the terms of the harmonic. So what about that one? It's got to diverge as well, right? Every term is greater than the terms of a divergent series, then that series must diverge as well. And this is called the comparison test. So you got two series, and you know that one of them is divergent, and the other one, all of its terms are greater than the terms of the divergent series. It's got to be divergent. It should make perfect sense, right? Now you're adding up a bunch of numbers that are all bigger than the numbers you were adding up before that were divergent. It's got to be divergent as well. Okay, but by the piece, so here p is what? P is 1/2, which is less than 1, which is also just by the p series we know it's divergent. But we used a comparison argument to talk about it. But you don't have to use comparison for this because p is 1/2, which is less than 1, and so that's divergent p series. So how would it go? Can you write out the comparison test for convergence? So what would make sense? Can you write out the similar, the flip side of the coin? If you were doing a comparison test that would show convergence, what would that be? Could you think about that and write that out? Mitch, how would you change this to make it for convergence?
Would it just be if instead of Bn being divergent, would Bn have to just be convergent?
Okay, so if Bn is convergent, I like that. Good start. Sorry, I don't know why it's selecting the whole thing. Okay, so if Bn is convergent, and?
Would Bn then have to be greater than An?
Okay, so
Or greater than or equal to?
okay, we're really talking about An. So then how would An have to compare?
So An would have to be less than or equal to.
That's right. Then An is
Convergent.
convergent. Now this is for all positive terms, right? So these are series with all positive terms. This should make sense as well. You've got a convergent series, and you have another series, all of whose terms are less than the ones that sum up to a convergent value. So what about the sum of those? Should make perfect sense that those would have to sum up to be convergent also. Here's an example of using the comparison test. Nope, not right. Sorry. So is this a p-series? No, but it's really close, right? So it certainly has the property of it, but p-series don't have a -5 in the denominator. They're just 1 over n to the p. Okay? So, but we can use p-series and comparison to figure this out. So what about 1 over square root of n? Is that convergent or divergent?
We can probably find an easier way of using the test by using 1 over square root of n is, it's actually greater than,
So what about 1 over square root of n? Is that convergent or divergent?
that is divergent.
Divergent, because n is less than a half. Now what about this one compared to 1 over square root of n? What about the terms of this? Are they greater or less? These terms are less than 1 over square root of n. Is that right? Smaller denominator. Greater. These all have a smaller denominator than 1 over square root of n, so therefore this ratio, all these terms are greater than . And if these sum up and are divergent, when you sum them up, then what about this? They're all greater than it. That's using this comparison test. So this is divergent by comparison to a p-series. Divergent by comparison to 1 over square root of n, because all these terms are greater than those. Okay. So got homework on all these